So now we are in a great position to apply the results Hille-Yoshida and Loomer-Phillips to a number of PDEs. Actually here I have 4 PDEs which I like to study, and I begin with reaction diffusion equations. We have seen reaction diffusion equations several times before already. So let's look at this model here. So we have ut is Laplace u plus f of t. F is a given function. U at x0 is u0, which is the initial condition, and then uxt is 0 on the boundary for x in the boundary. So then the function f is a given function which is continuous in time. The Hilbert space we are working on is L2, and the domain of A will be H2 intersection with H01. And so then from the little 0 here, we have 0 Dirichlet boundary conditions. So again, the boundary condition is in the domain. The set is dense in L2, as we discussed many times before. On this Hilbert space L2, the operator delta is self-adjoint, which is a calculation we have done before as well. U Laplace u, and then we do integration by parts. We get a minus sign, we do integration per parts once more. The minus sign goes away, and then we get Laplace u, comma u. And here this intermediate bit, this shows that this term is actually less or equal 0. So then the real part of u Laplace u is less or equal 0, and ta-da-ta-da-ta-da, we can choose again our growth bound to be 0. So then we, here I say it again, the omega is 0 there. And now we need to show that there exists a lambda 0, so that I minus lambda 0 identity, A minus lambda 0 I is on 2. And for this, we need to solve an elliptic partial differential equation, which goes actually beyond the topic of this course on function analysis. So this goes to a course on elliptic PDEs. And I can highly recommend a very nice book by Gilbert and Trudinger, which is only about elliptic PDEs. It's a thick book, I don't know, 500 pages or so. And there you can find all kind of conditions so that these solutions exist. So here for us, we just assume that such a solution exists, or that such a lambda 0 exists where we can solve the elliptic problem. Good. Let's do that, and then we can apply Loomer-Phillips to the operator ADA here, where A generates a strongly continuous contraction, a semigroup. Remember, omega was equal to 0, e to the delta t. So here's a semigroup for the delta. And solution for the reaction diffusion equation then can be found by our friend, the variation of constant formula. So then we get this formula right here. Beautiful. And then for regularity, we have used an argument for regularity for mild solutions, where we have shown that in some cases mild solutions are classical solutions. If you go back to that proof, then the same proof would apply here to show that u is C1 with values in L2 and C0 with values in dA. Right, so we have seen this construction many times, so that's a very typical solution space for semigroup theory. Let's move to the wave equation. So an example of a wave equation is right here. And now this has 2 time derivatives. UTT is Laplace u. We have one boundary condition, which I again assume to be Dirichlet, so equal to 0 on boundary of omega. And then we have 2 initial conditions, one for u0 and one for the velocity, which I call u1. And to tackle this problem with semigroup theory, we introduce a new variable for the velocity, which I call v. So v is ut, and then I can write the wave equation as a system for uv. So then I have uvt equals a matrix times uv, and this matrix is 0, 1 Laplace 0. So I just put a differential operator inside a matrix. And this matrix here, this will become our generator A with the domain of definition here. Okay, let's just a bit slower here. So first of all, the space I'm working on is H01 for U and L2 for V. And A will be the generator, this matrix, and the domain will then be H2 and H01. So here we see the boundary condition again. This is for U, and then the other one for V. So this is, let's say, for U, and this is for V, and this is for U, and this is for V. Okay. And again, the Sobolev spaces are dense, so that these domains are dense, so this is not an issue. So then a little proposition. ADA generates a strongly continuous symbol group of contractions. Yeah, we want to apply Luma-Phillips. On X, now X again up here is the space H01 L2. So we can use the inner product for H01 just using the derivatives, and for L2 we just use the integral. So then we need this estimate where the omega arises, U comma AU, which now in the vector formulation looks like this. We apply A, so then we get this vector to be V and Laplace U. And then we multiply this out with the inner product, so we get integral grad U grad V plus V Laplace U dx. And then integration by parts, ta-da, 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 will carry a minus sign, and so the terms cancel and we get 0. So then again, omega is 0. So then next we need to find one lambda 0 where we can actually find a resolvent, or at least where the operator is onto. So given fg, we want to find uv, so that a minus lambda I uv equals fg. Yeah, and guess what? This again leads us to elliptic theory. Here we come. First of all, it leads us to two equations. If you write this previous equation out, this one here, right, you get two components, and so you can write it out. You get v minus lambda u is f, and Laplace u minus lambda v is g. And now we can solve this for v and sub it in there. And then you get only an equation for u, which is then this one. Laplace u minus lambda square u is g plus lambda f. And g plus lambda f is L2. And so here we now use elliptic solution theory again, Gilbert-Trudinger, to find unique solutions whenever lambda square is positive. Good. That's all we needed. So we needed a lambda bigger than 0, so we can find a resolvent. Then we can apply Luma-Phillips, and we get a semigroup. And then this is just wonderful to write down the semigroup as this. So it's now e to the matrix 0i Laplace 0t. So differential equator, differential operator in a matrix, in an exponential, and this all makes perfect sense.